This is Chapter 5, Igneous Rocks, Lecture 2. So we're picking up now with more on the formation of igneous rocks. So this is a block diagram that shows you different areas in the profile of a volcano where igneous rocks might be formed. We have a source rock here, and there may be partial melting of that source rock. We have an accumulation into a rising magma body underneath the Earth's surface. Further rising could form a magma chamber. It can solidify underneath the Earth's surface or continue to rise. After that, it may eventually erupt as lava or ash. Now, melting might have occurred at, say, 40 to 150 kilometers below the Earth's surface, and that magma rises because it's less dense than the surrounding rock. It keeps going up. This is the source area where this material comes from. And what is the role of the source area? So you can have melting in the mantle, forming mafic, dark magma, dark minerals. If you have melting in the continental crust, you'll have a felsic or intermediate magma, lighter minerals, less dense and often lighter in color. The mantle is ultramafic, but partial melting produces mafic magma. And of course, continental crust will be more felsic if the source area is felsic. Continental crust will be more intermediate if the source area is almost completely melted. All right, so that's melting, but what about crystallization and crystal settling? So we have a chamber of magma. Felsic crystals are a little less dense, a little lighter. Within that magma chamber, they are going to float to the top and crystallize there, and mafic crystals will sink to the bottom. So as minerals crystallize, the composition of the remaining magma changes. So in this case, it might be kind of hard to see. Well, I guess you can see the lighter material on top versus the darker material on the bottom, which sinks. So this is like magnetite. It's likely to sink right to the bottom of that chamber. All right, so what about mixing? You can have two magmas mix together and form a new composition that would be intermediate between the two magmas. Like here, there's some sort of mixing. You can also have what's called assimilation, and that's where a magma incorporates the host rocks or the surrounding rocks into the magma by melting. We see that here. Now, viscosity is resistance to flow. Okay, so if you're more viscous, you have higher viscosity, you're more resistant to flowing as a material. All right. With high viscosity, if you had this lava erupting here, the material is very viscous, it piles up, it doesn't want to flow. Low viscosity lava spreads out far and wide. There's a difference in composition here. So felsic material, it's got a lot of silicates in it. It's very resistant to flowing. Abundant silicate molecules link into long chains that don't bend or move easily, so that magma is considered to be viscous. If you have mafic material that's low viscosity, higher temp, and it has fewer silica chains, it's less resistant to flow and it spreads right out. With this pileup of felsic material. It takes a lot of energy to break those bonds, so this can be a very explosive, destructive eruption, as in the case of Mount St. Helens versus the Hawaiian Islands, low viscosity eruptions, which just sort of flow. Still destructive, but not so explosive as is a felsic or intermediate magma. All right, so how can magma cool? It can lose heat to air, water, or underlying rock. There can be conduction into the wall rocks around the magma chamber. And then circulating water can heat up and rise and then be replaced by cooler water, causing convection, kind of helping the magma cool down and form igneous rocks. Right. And I've hinted at this before. There's a real relationship between the cooling rate of magma and the texture of the igneous rocks that we see. So with cooling that is slow, you get larger crystals versus moderate cooling versus fast cooling, very small crystals. Slow cooling then fast, you're going to get a mixed texture here. Larger crystals require more time to grow, so those form under the Earth's surface where rocks can cool more slowly. Really large crystals grow big because of slow cooling and the addition of water in the magma. And then glassy textures form due to very fast cooling, so fast that the crystal cannot form. It'll occur on the Earth's surface. Porphyritic textures like this indicate slower cooling at some depth to form the crystals, and then the rise of the magma to shallower levels where the matrix cools fast into small crystals or even glass. Okay, let's put some more of this together. So how could melting occur along a divergent boundary, like a mid-ocean ridge from chapter 3? All right, so we have this rising material. The solid asthenosphere rises to fill a gap. This is tied to decompression melting. So as this splits apart, we have this material rising. Huge drop in pressure as this opens up. Temperature could perhaps remain the same. And we have all this material melt fairly rapidly in terms of decompression melting. All right. Let's zoom in on igneous rocks in oceanic crust. And this is an idealized example. All right, you have the mantle to gabbro in a magma chamber to what we call sheeted dikes of igneous material to pillow basalts. Starting there, those are lava flows. They're extrusive. They're erupted into water. This is finely crystalline basalt. Okay, so we call those sheeted dikes. Gabbro forms from a magma chamber. The base of the gabbro is the base of the oceanic crust, actually. And then the mantle is going to be composed of ultramafic rocks. All right, so this could be similar to melting in a mid-ocean ridge. How could melting occur in a continental rift? So you have divergence within a continent. Again, melting in the mantle is going to be caused by decompression melting with a sudden drop in pressure as this area opens up. Melting does depend on the composition of the material, but if you have mafic mantle-derived magma, it can melt more of the continent as well. Starting with decompression melting, now going into something called crustal heating, heating of the crust. All right, so in a convergent area, melting in an ocean-ocean convergent boundary or a subduction zone, we have the plate subducting, and that increases temperature and pressure. But then there's also water supplied. This is really important in subduction. It lowers the melting temperature as shown in this familiar diagram, which causes melting of the overlying asthenosphere or mantle wedge, and that can rise up into volcanoes or an island arc of volcanoes here. And that'll be mostly mafic and intermediate rocks because of the composition of these materials. All right, so what about an ocean-continent convergent boundary? You have subduction again, and that adds water. It helps to melt the mantle. That rises upward and mixes with continental crust. This is mafic at first, but that mafic magma melts continental crust, which is felsic in composition. So you'll get mostly felsic and intermediate rocks in these volcanoes, or subsurface intrusive igneous rocks. So how does water get into a subduction zone? In this case, we have hot water circulating in a ridge. It can be added into pores and into minerals. Keeps going down further, subducting, and the water and the minerals is released at a great depth and rises as magma, or the magma rises from that. So during a continental collision, we also have melting. The descending crust gets hotter as it goes down. If it gets hot enough, partial melting will occur. There's going to be some water released during metamorphism here. But the magmas typically don't reach the surface. Shuts off there. Melting crust produces felsic rocks. You expect to see granite. Not a lot of extrusion here. Few volcanoes. Okay, hot spots. As in the case of the Hawaiian Islands, formation not along a plate boundary or a subduction zone. You have a rising mantle plume in the asthenosphere. I'm not saying why it happens, just saying that this is happening here. The mantle plume spreads out along the boundary. It causes melting of the overlying lithosphere. The boundary is between the asthenosphere and the lithosphere. And it continues to rise. And in the oceans, hot spots can form oceanic islands. On continents, mafic magma will then erupt as basalt. On continents, the hot spots can erupt explosively if the composition is felsic or intermediate, as is the case like with the Yellowstone caldera. And that ties into the viscosity and what it takes to break this material apart. It's going to be explosive and destructive, whereas the basalt flow is chill by comparison. Okay, so large magma chambers. These are some settings where large magma chambers can form. All right, we have an oceanic hotspot that can continue to melt through decompression melting. Same with the mid-ocean ridge, decompression melting. Subduction zones, you get magma there, aided by an increase in water and temperature. A continental hotspot is aided by decompression melting and further crustal melting by heating. Magma in a continental collision is mostly due to increase in temperature with that collision. All right. We'll talk about plutons, and in this case, that's magma that we see intruding, in this case, continental crust. Kind of irregular in shape. We can call this a stock. Now, it's usually steeply oriented like a pipe or a cylinder. On the surface, it might have steep boundaries that resist erosion. You can see it poking out of this landscape more than the surrounding rocks. Surrounding rocks are eroding away, but this pluton, probably granite in composition, it's harder to erode. Plutons can also form in sheet-like formations. They can be horizontal, vertical, or inclined. This is a horizontal sheet that's missing some of its original shape. All right, just like a big igneous intrusion of magma. You can have something called a batholith, which is one or more contiguous plutons covering more than, say, 100 square kilometers. You have multiple magmas emplaced over a long period of time covering a huge region, as in the Sierra Nevada batholith here. All right, when magma is injected as a sheet, it can be called a dike. This is a mafic dike. It cuts across a layer, or it's quite steep. All right. Now, a sill is parallel to layers, or it's horizontal, like so. This is the dike, by the way. And this is the sill. Magma can be injected as sheets. This is a laccolithic intrusion. So magma injects as a sill at shallow levels, and it forms a magma chamber that pushes up the overlying layers. This is what it might look like in a landscape. In the southwest U.S., it's usually medium-grained, porphyritic, and intermediate composition. This is Crested Butte, Colorado, though. And this is a volcanic neck. So you have a volcano, and then more magma is supplied into it, but then forms igneous rock within that volcano. Over time, erosion wears down the volcano. It exposes this more resistant rock, and it looks like a neck. Might look like this in a landscape. You can have it look like this as well. Another volcanic neck formed well beneath the Earth's surface, but it can be uncovered by erosion of overlying rocks. This is Shiprock, New Mexico. It wasn't formed inside a volcano, but at depth below the volcanic crater. And it's what's remaining of all this other stuff that used to be over it. You can also have jointing exhibited in igneous rocks. We call that columnar cooling joints. That's what happens when you have a hot but solid igneous rock contracting as it cools. And usually those columns have 5 or 6 sides. They look really stunning. This is in Oregon. You can find them in Montana as well. Happens when it cools. I mentioned the Sierra Nevada batholith briefly. Here's a block diagram of that. The granitic rocks and gray form most of the mountains, but the batholith varies a lot in composition. The green rocks here are metamorphic. They were baked and heated by the batholith itself. All right. And then we have much younger volcanic rocks in red and pink, and then recent sediment that was deposited over it. There's also a fault along the east side with a sediment-filled basin. We call that's the Owens Valley. And this is kind of how it formed. This is the setting of the Sierra Nevada batholith, we can think about all the igneous processes that could occur here. So you have subduction and melting. Water helps the melting process. Form mafic magma here as well. That's your future Sierra Nevada. It's the source for the magma, right? That melts the crust. These magmatic processes caused more magma to evolve over time. And then we get mostly felsic and intermediate rocks. So we started here. A lot happened to get us to this Sierra Nevada environment. And we'll stop there for this chapter.